Hi everyone, so we're going to pick up where we left off on images that come with lenses. We're going to do a quick summary of what the ray diagram showed us earlier, and then we're going to move forward with an example and then the lens equation and one more example. If there's time, we'll try to do ray diagrams for a concave lens. If not, that'll be another one. So if you look at image properties, that we found from the ray diagrams as a function of object location. Just like a mirror, you will see that there is a pattern. Okay, so we're going to start with location of the object. If it is at, or if it's very far away, then the image location is at F. So in other words, the rays come in parallel, and it's smaller than the object, and it's the smallest possible size you can get. It's inverted for I, and it's real R. All right, now we go closer in. So if I do just a reference, here's our lens, here's F, here is C. We started out here at infinity. Now we're going to move in somewhere, let's say right here. Let's going to move somewhere like there. Sorry, this pen is not working properly, which is really annoying. So right here, maybe it was working a second ago. All right, so what do we see from that? Well, we got an image that was away from F, but not quite past C. So we can say that SI is greater than F. That should be a greater sign, sorry, and less than C. The size is still going to be smaller, okay? It's still going to be inverted and real. And then we get the crossover point. So we moved the object to C, then the image is at C. It's the same size, still inverted, still real. So in other words, the image would look like this. It's directly overlapping it, same size. I haven't drawn that very well. Then when we move between C and F, okay, our object is going to be greater than C, okay, Beyonce. Potentially way out here. And importantly, it's going to be magnified. So I'll just write magnify. I don't have space for the fied. All right, and it can be much larger. It's still inverted, still real. Okay, now we're continuing to move closer and closer. So I just did this case here where the object is here. Now we're going to move the object inside of F. Okay, so if we're inside of F, then our location is, if you will, on the, I'm going to say negative SI. We're going to have a negative image distance. In other words, the image is going to be on the other side of the lens. Okay, so your eye generally will see the image, the real image is over here, inverted, but now it's going to be on this side. So that's why I'm going to put it like that. And it will be magnified. So I'm going to put a big M for magnified. And it's going to be upright, U, and it's going to be virtual. Okay, and at F, right, if we put the object, I know this is getting pretty messy. If I put the object at F, then we don't have an image, all right? So no image, it's a blur. So we want to see, basically, as our object distance gets smaller and smaller and smaller, our image distance gets bigger and bigger and bigger, and the crossover point is at C, just like it was for a mirror. So nothing surprising here. Okay, so if you're given the following, converging lens with a diopters of power. All right, I'm just going to skip to that. That's just the focal length. I did the math, is 30 centimeters. Is used to make an image 1 centimeter tall for an object that's placed 50 centimeters away. And this is the scale. Okay, so we are going to place the object, and I'm going to pretend I'm going to draw it 1 centimeter tall right here. And I now know the focal length is 30 centimeters because I did the power one. So I'm going to label that F. And I'm going to put C right here, which will be double that. Okay, that's supposed to be C, and that's at 60. And I want to understand what the image is going to be. So that should be pretty straightforward, I think. I hope I can draw this. So I'm going to come in parallel. No, maybe not, because I thought I had a line. Stupid thing. There we go. That's what I want. Okay, let me try that again. So I'm going to come in parallel. And again, I'm standing at an awkward angle, so I'm going to assume that parallel. I'm going to put an F for reference right there. Okay, so let me go back to that. And it should then bend through F. I'm just going to extend that out. And then I'm going to have a line go through F, stop there, at least the arrow. I'm not going to go to the tip. And then come through parallel. Okay. And to my eye, yeah, that looks about the most parallel from the, I don't want to stoop down. So if I go ahead and draw the image, then the arrowhead image is going to be right there. Okay. Now, I don't have a ruler to measure it, but the image location seems to be at 10, 20, 30, 40, 50, 60, 70, between 70 and 80. So I'm just going to put image location about 75. Okay. This is acting really weird right now. Putting arrowheads and everything. How tall is the image? I don't know. The way I drew it, I'm going to say it's about 2 centimeters where I started at 1. I get give or take. What type of image definitely looks real? Okay, I know it's real because light converged there, and it is inverted. So we want to be able to do that. It's pretty straightforward. Now, could we figure this out using an equation? The answer is yes. We can use the lens equation, which is the same as the mirror equation. 1 over S equals 1 over S I plus 1 over SO. Okay, and again, a virtual image, then the image distance SI is negative. So be careful of that moving forward, because sometimes you're told where an image is, and if you're told it's virtual, you better put in a negative value for that. And linear magnification, again, is the absolute value of HI over HO, which is the absolute value of SI over SO. So let's apply this to the problem I just did using the ray diagram. Okay, so let's apply it and check the ray diagrams. So if you recall, F was 30 centimeters and SO was 50 centimeters. So let's see what magnification we get and where the image distance is. So I would say I'm going to just solve for image distance. 1 over SI equals 1 over F minus the object, 1 over the object distance, which is 1/30th minus 1/50th. All right, common denominator would be 150, so this would be 5 over 150 minus 3 over 150. Okay, hopefully you can do that yourself. That's 2 over 150. Therefore, SI, if I take the reciprocal, is going to be 75 centimeters. Okay, and if I go back to previous one, I said it was around 75, right? It was between 70 and 80. You might argue closer to 72, but my rays weren't perfect. So that's nice. We got verification there. And if I look at the magnification, I could say magnification is SI over SO, right? I don't need to worry about absolute value. So SI is 75, the object distance was 50, that's 1.5, and that's roughly what I said. I think before I said 2, close enough if we had measured it. All right, so nothing startling different here. Just keep in mind when you're looking at a lens, this pattern, but when you're looking through the lens, your eye is on the opposite side of the lens as the object. Okay, you're looking through the lens to see where the object is, and it appears to be right there. Okay, so make sure you can distinguish between object and image. All right, so what do we do for a concave lens? And this is a doubly concave. Well, it's very similar to a convex mirror. So we can do 3 light rays. One is pretty easy, and I'm going to do the third one. Light passing through the center of the lens continues straight. Okay, so there's nothing startling about that. All right, parallel light refracts as if it originated at the negative F. Okay, well, so I got to be careful here. These are both negative Fs. So what I can say is if I have a ray coming in parallel, which I've drawn here already, it refracts. We know it's going to diverge in this general direction. So it's going to diverge as if it came from this. So I'm going to diffract it up like that. Okay, so watch this if you didn't follow. But if I trace this ray back right here, it should pass through negative f. Okay, and then the other one is if I have a ray that doesn't pass through the focal length here, but passes heads as if it's going to go through this point right there, then it's going to bend parallel. Okay, so remember your eye is on the other side of the lens as the object. So where does it see? And if I do the third one, let me do the third one. I'm going to go straight through the heart of the lens. So your eye doesn't see any of these rays ever converging. But what it might pick up, or what it does pick up, I should say, is it looks like the rays came from a common point of origin. So if I trace this back, wish I had a different color. Let me see if I can get a different color here. Let me try red. Might be real fat red. But you get the idea. I don't think this is really helpful. Too fat. Yeah. Well, you get the idea here. It's going to converge. Sorry, I'm stuck now as to what to do. That's a little bit better. Boy, I'm making a mess of this. I think you get the idea. Right, it's going to form the image right here. Okay, and we can see that it is virtual, it's upright, it's smaller. So the image properties, there's no change amongst where you place it. So as you can see, always forms the same side of the lens as the object. Okay, that's kind of like saying behind the lens. Size is always smaller. And the orientation is always upright. And it is virtual. Okay, so the last thing that we can talk about is corrective lenses. I will actually do that in class with you because I got some demonstrations to go with that. So if you have any questions, bring them to class. And I apologize again for the not very good rendering of this image here, but we can talk about that in class as well.